We've got the recording going. Welcome back. So we had a big session last time with Jonathan, and we covered off a lot. This session, we're getting into more of the details: drainage, geometric design, lighting, pavement, all the sorts of wonderful stuff. So I'm going to have to move to Jonathan pretty quickly. I just wanted to cover off a couple of things. So thank you for those who jumped in and did their quiz. We apologize. There was a little issue with one of the questions, which thank you for quite a few people pointing out. And if that caused any issues for you getting a pass or anything like that, Marissa has gone through and adjusted, but please get in contact with training at Safe System Solutions if there was any issues. But you've all done really well on that. There will be a quiz at the end of this module as well. Very similar, and so you'll be able to take your learnings from this session and then apply them in a quiz at least, and then out there actually designing raised crossings. Just a reminder also that the raised crossing principles course, and we've got the recording in there. There's some important stuff in there that we're not covering in these sessions that you really should be across. And of course, a really important principle of the principles course is that raised crossings are an amazing safety feature. And we're talking in the details of design here and how we can get them in and do the best job possible. But it's always important to step back and say, well, is it better to have nothing, or is it better to have to have compromised a little bit on some of the design specifics? And most of the time it is better to have something that is a bit compromised here and there rather than abandoning the whole treatment. And so take the principles Jonathan's talking through, learn the details of the design, and then really think, as we do as designers, about the context and how we can adjust and massage and manage things. So I think it's really important that we do remember that these are incredibly safe features compared to an at-grade pedestrian crossing. So raising it or slowing vehicles on the approach, so important. And Jonathan's really getting into how can you best do this with all the drainage, geometrics, pavement, and all of those exciting things. So on that note, Jonathan, I'm going to hand over to you. I can see your slides on screen beautifully. Marissa's there in the background. I'm monitoring the chat. Let's get into it.
Fantastic. Well, yeah, welcome back, everyone. Really excited to be here again today, of course, to go through our more detailed design components. So, of course, in day one, we had our scoping and our site validation, and that's, turning what we wanted and trying to understand if our site may be suitable for that. In day two, we are going to go through the drainage design components and the geometric design side of things. We'll be looking at simple and complex scenarios where perhaps our site validation process said, oh, this might not work so well. So what geometric design solutions might we have to look at? We're also going to delve into the pavement design principles. And as I suggested, in day one, a couple of days ago, it won't be about pavement designs and how to design your pavement. It's about what changes at a raised safety platform in terms of pavement and what are some of the key risks or things to consider in your pavement design solutions. And then we also have a lighting design component, and today is so jam-packed with great nerdy design details that our lighting component will be made available to you on the learning management system as an offline pre-recorded course. So if you are very, very interested in the lighting design component, please watch that, and that will be useful for your project, even if you're not potentially a lighting enthusiast as much. So what I'm talking about today is the fundamentals of actually designing our raised safety platforms. And let's jump into drainage design. So that is, where is our water going? I mean, a raised safety platform forms a barrier to many, many surface flows, potentially at least. And even in a scenario such as this, where we've got the curb flowing potentially this direction, this acts a bit like a dam wall. So we need to understand, what is this system going to do in terms of where water is going? It's a key component to our design. It's actually a key part of scoping our projects, and we need to make sure that we have the appropriate solution for our drainage for every project. So jumping into the options that we have for drainage is, of course, avoiding stormwater. And I'll just jump into the next slide, which is a similar image there. But what I'm talking about is potentially the lucky, very rare scenario, but it can occur, where you are at the top of a crest area. And that means that water falling on the pavement surface just flows away, and there's no additional drainage requirement for this site. That's like I said, an existing scenario where you're at the top of the crest, or you're close enough that you might be able to just tweak out your design to shift across a little bit. I mean, it can occur, but it is rare. But there's other scenarios in which you can achieve, and I have avoided stormwater design solutions. So let's have a look at those. You can utilize existing flow paths. By that, I mean, and this is an image that we used in day one. This is our little threshold crossing treatment. And a site such as this has the existing curb line, like I talked about, being used for a drainage flow path. Rather than water going around the corner and potentially becoming trapped at a setback arrangement, the water is enabled to flow continuously. There's a little bit of water ponding here, and that's the bluestone issue potentially. I'm not suggesting that you do a threshold crossing to solve your drainage problems. I'd say that where this is positioned is a separate issue. But if you're doing it in a threshold location, you should consider this as part of the design process. And hopefully you can achieve that scenario. And the same site, I mean, it has something else that I really love to see, and it's hard to do, particularly if it's a setback arrangement. But in this image here, again, there's a little thing going on, and that is that we've been able to utilize an existing stormwater pit. So this is an existing side entry pit, and we've been able to position the toe of our ramp at that side entry pit, meaning that it's able to be used with no additional drainage design costs. It's just working as is. Again, that's a rare scenario, and when you're out on site and when you're scoping up your projects, you will time and time again be looking at an existing side entry pit that's right near an existing crossing location and thinking, oh, can we use that? And you'll find it's a disappointing feeling when you realize that a lot of the times these are positioned really close to an existing crossing, and when the ramp sections are constructed for our projects, these need to be converted to a junction pit, and perhaps another side entry pit is positioned prior to the toe. I'll be talking a lot about positioning of side entry pits and other drainage solutions shortly, so yeah, that'll be good for anyone interested in that. So moving along into, again, avoiding stormwater solutions, there's other opportunities in our projects, and these are in the more full reconstructions, new road environments. But an option such as this, where we have a side entry pit on a side road at a low point, and that's required because otherwise water would just pond there. The side entry pit, again, in a parking bay potentially, and this road environment, just as an example, it's flowing at 0.5% in this direction. And then we've got our raised safety platform, a wombat crossing in this example. And again, with the 0.5%, it's flowing to new locations where water would catch against the toe of this system here. That means we've got to then grab this water in two locations, with two other side entry pits, and flow them into the network that we're designing. But if it is a new road or a full reconstruction or major rehabilitation project, even potentially just a minor rehabilitation project, there are other opportunities as well to reduce our drainage networks. And keep this in mind for your projects, because with a simple shift in what we're thinking about, I could then say, actually, no, I don't want to catch the water here. I'm just going to grade back at 0.5% again. Perhaps have a little vertical curve in there. It may not be 0.5%, it could be a range of longitudinal grades, but I could grade back and just utilize these two necessary pits that were catching water anyway. And in doing that, I've reduced my whole system and the cost of the system, including pipe networks and pits. I've reduced that to a simplified network, even potentially reducing maintenance costs, etc. as well, as there's less pits to inspect into the future. So jumping into one of our summary slides, as with day one, I will be presenting these summary slides. I won't dwell on them, so I'll just leave this here for a few seconds now, and then I'll move on to side entry pits. So side entry pits are a fantastic piece. Oh, sorry, Ken, yes, before we move on.
Oh, yeah, there was a question that came in. In the first scenario, what happens if it's a B2 curb, a barrier curb? So the first scenario, which I'm not 100% sure which scenario that was referring to, but maybe that makes sense to you.
Not entirely, but I'd say that a B2 curb or an SM type curb wouldn't make a huge difference. If you could get clarification on the question.
Yeah. Fantastic. The one with the bluestone curbing pictures. Thanks.
Oh, sorry. Sure. Yep.
Yeah. Okay, it will be the same, wouldn't it?
Yeah, it would be the same outcome. Yeah, this is actually a bluestone B arrangement, so it's a B type arrangement here as well. And the way that we flush into our ramp section wouldn't necessarily change a thing. Yeah.
Now, there's another question here, and I'm this one I was starting to dig into because I don't actually know the answer. Is the RRPMs there? Are they an optional thing? I see some people use it. I suspect it's used where you feel you have a little bit of a low light situation on the approach to ramp. But do you know, Jonathan?
Off the top of my head, I don't, and so we'll definitely take them on notice. Maybe on a different day, I might have.
I'm going to give Dan. I'm going to give Dan a prize for asking asking the question that I've been asking, and he's done the same thing I have, which is digging into 1742 to try and answer that, which it does not answer. So I'll keep digging into it, and with these sort of things, happy to email out to the group when we find an answer. Back to you, Jonathan.
Fantastic. Okay, so let's move along to our side entry pits. And I've set here standard side entry pits. I'll also be talking about other varieties such as in-road pits shortly as well. Side entry pits are a fantastic system. I'm just going to run through how they operate just quickly so we all get a head around some of the key features of a side entry pit. And that is, I've got a plan view here and an elevation over on the right-hand side. And in the plan view and the elevation, a side entry pit has a lowered invert right at the side entry pit itself. And so that's over here. And what that lowered invert does is it increases basically the height of the inlet or the gap here at the throat. And that means it's less likely to block, which is fantastic. And it also have, to get to that lower invert, some what's called a transition length or transition in the curb invert. That's where it pushes down from typical curb invert level here to the throat invert. That has the added benefit of rushing water towards the pit as well. And that all adds together to why side entry pits are a fantastic piece of drainage infrastructure, because that lowered invert and the drop into the pit means that they sort of self-flush and they self-clean very well. By self-flushing and self-cleaning, I mean that litter that builds up at the throat gets pushed through and it doesn't sit at a similar level to the invert, actually drops into the pit. And it takes very leafy environments for these to become a maintenance burden, even though they may require maintenance. It's not so much likely to become a burden in itself. So side entry pits are fantastic. That lowered invert is a key component in how they operate. So moving into a bit of a quick question and quiz is, and I think this is just in the chat window, but if you could spam into the chat window for Ken's enjoyment, whether or not we think that a side entry pit placed behind curb hard against the toe of the ramp is better than, or where would we like to place one, or do we offset it a little bit from the toe of the ramp? So A or B, just spam into the chat.
A or B into the chat. We'll have a quick deluge of A's and B's coming in, and I'm gonna we got a lot of B seems to be a little more popular here. We've got a few A's in there as well, though. Yep. So it looks like more liking B, but what do you say, Jonathan?
I say that, well, that's great. And there are scenarios in which you consider both. And what I wanted to do today is, A, looks like a very attractive option because it's hard against the toe. And that means that, yes, like the water's going straight into this pit. What I'd like to do is just chat through how these operate at a drainage level first. And then I'll basically highlight that I think either have merits, but certainly that offsetting it may not be such a problem if you were concerned about that. So in the option A here, I've got this blue area, and that's water that's sort of flowing down crossfall and longitudinal grade. And it comes to the toe of our ramp here and flows along the toe of our ramp and then finds its way into the pit from the toe of the ramp. So that's the water that misses the pit, hits the raised safety platform, and goes straight into the pit. So that's great at a drainage level. Then we've also got water that flows sort of the same arrangement down the crossfall and longitudinal grade to the curb line though, or directly into the pit. So this operates really well in terms of where the water's going. Got no issue there. Then on the right-hand side for our option B, again, we've got the water that flows to the toe of the ramp, down to the curb, and then actually back to the pit, though, via those transitions and our inlets. So whilst there's some longitudinal grade here, that then at the invert transitions back to our lowered invert at the pit. So that works nicely. Again, we've got water that flows to the curb and direct to the pit. And then we've got this tiny little area here that does something slightly different, but basically a small area flows to the curb and then back to the pit. And to be honest, any concern for this being over capacity, if you were able to grade it out, I wouldn't worry about it because this operates in a very similar manner. This is not a huge amount of water for just a standard setback such as this. And I'd say that either option has good drainage performance and has merit. Now, what I'd like to do though is I'd like to chat through these arrangements again with a little bit more detail about how it works in terms of operation for our race safety platform. So here we agree that we've got good drainage performance for an arrangement where it's hard against the toe of the ramp. But what's actually happening at the very invert that's been lowered at our race safety platform at the invert of curb, we have that, I'm using an example here, it's from the industry design manual. It's 40 millimeters lower in this example at the throat. And what that means is that hard against the line of curb at the invert, we've created a platform that's actually 140 millimeters high. So hypothetically, I'm talking, of course, about a 100 millimeter high platform here. And we've added 40 millimeters to that height. That's an issue for someone tracking hard against curb. It's not a huge concern for me. I wouldn't say this is a void option for a drainage solution or it has significant issues, but it may be something we want to consider. At the lip of curb here, though, look, we're back at existing surface level. The pit is not affecting the lip of curb levels at all, and we're back to having a 100 millimeter high ramp. So I'd say I'm only concerned about this situation where we've got very thin traffic lanes at a race safety platform. So if you're down to your 3.1s and you're sharing cycling and vehicles through this area, then perhaps you're increasing the likelihood of someone driving along the channel portion of curb, and you may have increased ramp height effects. Probably not the full 140, because it's very hard to be hard against the curb with your tyre scraping along the edge. But you may be having increased effects of the ramp of the platform height. And again, a standard 300 millimeter wide channel, not so worried, but if you're in an older environment that has some of the previous standards for channel widths, and that can be, that's 450 is very common. It means you're more likely to have someone tracking in a lower section. And even 600 millimeter channels are out there, and that's what I'd be saying, oh, this actually might affect the ramp height for someone who's tracking nowhere near the line of curb. Moving along though, I'll use a similar image for another example of our offset pit, which is offset by one transition length. For this scenario, by the time that we're back at the ramp toe, we're back at the 100 millimeter high system. And yes, a tyre sitting, so looking at our elevation here, perhaps a tyre sitting down in this location is still feeling a slightly higher ramp, but this has eased it for us and has made this issue, it's relaxed the issue for concerns about bottoming out or changes in ramp and platform heights. We've also got the reality that if you ever look at how this is grading back, and in this example only, it varies depending on your site and longitudinal grade, but we have 1.5% longitudinal grade coming down here. And if you draft this up for this specific pit, we're grading back at 2.5% along the inverted curve, just along here I'm highlighting now. So that grades back at 2.5. That's significantly exceeding our minimum curb grades. So in theory, you could actually position this pit further back if you were concerned about potential issues with bottoming out. And again, with a back of curb side entry pit, this is a minor concern. I'd say it only applies to thin traffic lanes or particularly wide channel sections. Now, there are, of course, limits to how this operates. And I was talking about how that grading back scenario works. And let's just use this as an example. If you were at a site that had 4% longitudinal grade, and yes, those of you from recalling from day one might also be thinking immediately that, well, that's got some other issues. That's quite steep. It might not suit our crossfall for our path users. But still, if you're at 4% longitudinal grade and you can resolve this in other ways, then when we have a look down here at what that means for our setback system, well, it no longer flows. So that's where the limits for this operating correctly are in our longitudinal grade, and this would no longer work, and that means you'd have to be looking at placing this hard against the toe of the ramp. Okay, so let's move along and now start to talk about in-road side entry pits. So just using over here as an example, that's when the curb here, and this is the back of curb, and this is the road side. An in-road side entry pit is placed within the road itself. They operate in a similar kind of manner to a side entry pit in terms of a standard side entry pit behind curb, in terms of their drainage operation. So once again, we've got the invert lowered, but it's also the cover itself is lowered. And that means that, and again, you can see over here that this whole section here is lowered. And then we've got our invert transitions, which is very similar, but also actually transitions within the pavement itself to stop there being a sudden bump here or like effectively a pothole in the road. So the transitions work in the curb and within the pavement. They operate really nicely by doing this, by lowering the whole pit lid itself. We have a lowered invert here. And so this again self-flushes really nicely, and these operate well at drainage level, and they're relatively low maintenance. You might be thinking, why would we even be considering an in-road side entry pit? And there could be a range of services or other impacts behind curb that mean that a behind curb side entry pit solution is not going to work for your project, or perhaps you'd like an alternative to work because it could be better outcome. But there's an issue here that I don't love, and it is specifically, I don't like it for our race safety platforms. And perhaps in the chat, just very quickly, can someone tell me what I don't like about this system?
So we've got some good comments as people pop their thoughts in there. A couple of really good comments around drainage and some of the practical implications, street sweepers and capacity of side entry pits and the like. So that's been good. Thank you. What do we got here? Depth next to ramp, driving on top of it, changes in road geometry.
I'd say depth next to ramps, probably covering the concern that I had there. And thanks everyone for popping your thoughts in there. And if you've got any other great ideas that popped up, Ken, perhaps you can bring them up after I have a chat through this scenario here. So my key concern here is that, we've got this lowered pit lid now. And that means that whilst the behind curb example of a lowered invert potentially causing issues for our platform heights, that was pretty much limited to the line of curb location or the inverted curb location. Unlike that, with an in-road pit variety, you may find yourself having a lowered pavement level, beyond the line, beyond the lip of curb, and actually within the road pavement itself could be lowered. And I'm going to use I've drafted this up just to illustrate some of the major issue here, which is that when I draft this up to the exact standard requirements, and I look at what these levels are, I'm looking at the invert here, and I'm looking at, well, actually now I'm in the pavement. This is 85 millimeters lower the line of curb. I mean, that's turning a 100 millimeter high platform into potentially 185 millimeters. And that's huge. I mean, that goes beyond any guidance for race safety platforms throughout Australia and New Zealand. And even beyond, so that's the rarer scenario. The 185 is the rarer scenario where you're tracking right on line of curb. But even at the lip of curb, where you can expect vehicles that are regularly tracking, we are potentially 57 millimeters lower. And that's raising it again by something that's higher than any guidance out there for how high this system should or could be. And that means that our issue is no longer restricted to thin carriageways, and that an in-road side entry pit may, for the average vehicle, be dramatically increasing our platform heights from 100 millimeters to something that may result in a vehicle bottoming out. And I'd say that significantly raising our platform heights is a key issue. We'd be really reluctant to recommend this as a great drainage solution. And you may be able to consider these for your project. I'm not saying it's unacceptable, but I'd say I generally wouldn't recommend an in-road side entry pit. I'd also use this moment just to comment on the reality that I don't know every single jurisdiction or standard drawing in Australia or New Zealand, and that there may be systems out there that are in-road variants that reduce this issue. So you might have perhaps a bent lid scenario. I've seen some graded pits that have something sort of like that, not exactly like that. But there may be options that are in-road that are available, and I'm not aware of a system but that works perfectly. But typical Vic Road in-road side entry pits such as this have this issue, and please be aware that this could be a problem for your project. And I'm just going to move to the summary slide, and then Ken's going to ask me a question.
Yep. Would curb outstands or curb build outs help in some scenarios with that issue?
Potentially. It's an interesting question, actually. So I'll just refer back to here. I'd say that, and I assume what you mean is to send the curb back a bit further. And actually, if I go to a plan view.
Out a bit, I would imagine. But
yeah. I won't go to plan view. It's a bit too far back. Building it out.
Yeah.
I mean, it could, but I'd suggest that if you have the room, the carriageway width to build it out and have curbs sitting further out ahead of this, then you might as well just keep the curb. If that width is acceptable for your design solution, then shouldn't it be acceptable potentially for your race safety platform carriageway width as well? And then you could put a back of curbside entry pit in place. It's an interesting question. I'm not sure if I've fully understood it, but I think I've understood the situation there, and I'd suggest that that you consider an in-road side entry pit because you can't build behind the curb, and if you could have curb in front of it, then you sort of can sort of
Yeah. All right, let's keep kicking on. And
yeah, sure. So there's our summary slide. I'll just leave it up, but again, just highlighting the issue that an in-road side entry pit may significantly affect our ramp heights and platform heights.
And of course, people can download the PDFs of the slides in the learning management system. So those summary slides may be something you're referring back to at a later point. But talk to us about curb outlets.
Great. Okay, so let's jump in and talk about curb outlets. It's another option for our project. They've got some issues, and we'll be learning about those shortly. If anyone doesn't know what a curb outlet is, it's this section here. And how it operates is that water just flows along our curb or along the toe of our platform here. And this flows directly to roadside drainage. This roadside drainage may be a greater pit, like what we're looking at here. But there are other options. So we could have inlet catch pits. It could be flowing to swales and V drains, existing or constructed. May also just be flowing to one of our localized water sensitive design solutions. So this might integrate water treatments for your project. And they've got some good things, they've got some bad things. I'll jump straight into some of the bad things. I'll talk about the key issues here. And that is that these things outlet at invert level, and they don't self-flush like a side entry pit, and they actually block up very easily. And some jurisdictions actually have policies that say don't use curb outlets because they are a maintenance burden. If you don't have a system here where it's beached and paved behind the curb outlet, then these just grow up because debris starts to catch up and plants start to grow, and they become dysfunctional quite quickly. If you were to have a steeper section here for your curb outlet and it was beached, then that's a better maintenance arrangement, certainly. So I've got a little question for you all popping up here, and it relates to our curb outlets, and it relates to what how they may operate. But it might look a little bit confusing, but pop into the chat if you could what we're looking at here.
Oh, okay. Pop in the chat. What are we looking at here? Could be anything.
And I won't give you too long because you might not get it, or you might jump straight into it and understand what we are looking at.
Okay. Well, we've got a few answers are coming in. We've got, they're coming in thick and fast now. Brass, covered, blocked inlet, blocked grate.
Blocked grate, big win there. Blocked grate is correct, because what we're actually looking at here when you stick the heel of your boot around the ground and push away the debris is we're looking at a greater pit that had been blocked up. And
prize for Darren there.
I think that's right. Absolutely prize worthy.
Great.
That's it. And it's to illustrate the point that greater pits, they don't self-flush and they block easily. And they might seem like a great roadside outlet solution until a few years later, in this case, a long, long time later, they're overgrown and no longer operate as intended, at least. So they can be a big maintenance burden for our projects. You might find yourself out there many times a year, not yourself, but your crew or your project maintenance leads out there many times a year, clearing them of debris. And greater pits aren't the only solution that we can connect to, but when you've got a system such as a curb outlet that is a system that may be a maintenance burden, may block up itself, and it flows to another system that may block up, well, that's sort of doubling up, and it got some concerns there. We can also connect, though, to something that's a bit more maintenance friendly, and that's our inlet catch pits. Inlet catch pits work a little bit like a side entry pit, where we've got, again, water flowing along into an opening. And this is our plan view here, so potentially down a table drain, but in our case from potentially a curb outlet, flowing into an opening in the side. And that drop there and the higher opening levels here mean that it can self-flush and it can self-clean, and it's just less likely to block up. So this is from a VicRoads standard drawing. And what we're looking at here is it's suggesting 150 millimeter high to 300 millimeter high sections here. And 300 millimeters high would be unlikely to block. That's great. But that height then has some issues, particularly for a race safety crossing location in the roadside. If you've got something that's that high sticking above the ground, then we've now got a tripping hazard concern. I'm not saying that these work everywhere. But we are potentially putting something in a desire line where someone might be walking towards a crossing, not directly down the pathway, and this system could cause an issue for us. So if we're going to consider these near our projects as an alternative to a graded pit, I'd be saying consider potentially reducing this to something a lot more considerate of tripping hazards. And whilst it might not be conforming to this drawing here, I'd be saying that around 100 millimeters is better at a tripping hazard level than the recommended 150 to 300 here. So as I erred towards earlier, we've got curb outlets blocking easily, and they connect to other drainage systems that block, or they present tripping hazards. And what that means for our project is that why are we considering these? They've got issues and they may not work that well. Well, why is Jonathan even talking about them today? And the truth is that, well, like any piece of drainage infrastructure or infrastructure out there, there's reasons and there's scenarios at which it works better than alternatives. So let's have a look at this image here, just to illustrate a standard side entry pit scenario. And what we've got is potentially a graded pit that's going to block up our side entry pit here, connecting to it, or maybe this is just a junction pit. And in this scenario, unfortunately, our pit clashes with a gas service coming through. So this gas service is, say, 400 millimeters deep. And no matter what pit arrangement we put, even if we decide that we can justify an inroad pit, well, our pipe's going to hit that gas service, we're in trouble. So in this scenario, a drainage solution is challenging. But when we look at our curb outlet arrangement, well, our curb outlet outlets at the invert level and goes over our gas service and connects to potentially an inlet catch pit or a graded pit that's maintained regularly. So this can assist us in avoiding, so curb outlets can assist us in avoiding roadside impacts. And it's not limited to our services. It's trees and other things that make potentially excavation a challenging thing to get a successful result from. Our curb outlets might be the best solution to get water out of the curb here. In this scenario, for instance, I'm also showing it beached, just as a nice friendly reminder that beaching is what you really want to be doing, I think, to avoid the maintenance issues that curb outlets may present. I also say that in this scenario, we've got 2 pits and some pipe, and yes, curb outlets, I mean, they might be a cheaper solution, but don't jump on cheaper being cheaper life cycle costs, because maintenance costs may be significantly greater for this system. So I'd say that if an alternative drainage arrangement doesn't work, then yes, this is a good solution, and it's got the added benefit of potentially being a cheaper outcome for you. Okay, so moving on to our summary of curb outlets. Again, as per usual, I won't be dwelling on this, but we've got a range of highlighted in red issues for you to consider if you are considering a curb outlet for your project. Okay, let's move on to one of certainly Victoria's favourite treatments for drainage at a raised safety platform. That's our gutter bridges and our box drainage. And by box drainage, I mean graded pits or even box culverts themselves. Graded pits, graded channels, and box culverts potentially. These are very, very popular at the moment, and they've got some issues. They've also got some great things that they can achieve for our project. So let's just jump in and talk about the types. So here's what I mean when I say gutter bridge. It's typically from an existing curb to potentially a newly constructed piece of curb in an outstand or something. And this is bridging the gutter area. Then we've also got our box drainage. So it's a graded trench in this example. That's very, very common in these sorts of treatments. Let's have a quick chat about locations as well, just so we can get our head in the space of understanding where these may be placed. We've got our hard against traffic lane, so that's in the flow of traffic here. Not in the flow, but you understand what I mean. It's on the edge of the traffic lane. And then we can also place it behind a curb extension such as this. So our actual raised safety platform is beyond the image here to the right, and this is placed at the back of our curb extension with some parking bay curb extending beyond. And that pretty much summarises the positions that we can place these in. So let's get a bit more interactive again, and let's have a look at this arrangement. We've got on the edges of our traffic lanes some systems here, and a system over here as well. And I just want to ask you, just with a thumbs up or a scary face, what or do we like this? Are we happy with this?
While you do that, so people can put their thumbs up or their scary face if they Just wanting to get some clarity on the term beaching that you used
Oh,
earlier.
of course, apologies, guys. Yeah, certainly. I guess sometimes I wander off into my nerdy world of design and engineering, but beaching is effectively placing of stone, typically I'd say in these areas, grouted rock. And I would just use this image as an example. It's not necessarily bluestone, it could be quite small rock. The beaching means to make it a sort of semi-paved surface or a rocked surface. And what that does is it typically is placed to reduce scouring, so to reduce erosion and things like that. But it also means if it's grouted beaching, so you've got cement or some form of grout between the stones, it also means that plants just won't grow there. So it serves a double purpose of reducing erosion and also avoiding that maintenance burden. Not avoiding, sorry, incorrect term there, reducing that maintenance burden for curb outlets. Hopefully that assists there for you.
Yeah, that's great. Thank you. And we're getting a lot of scary faces. There's some comments coming in the chat about different issues with it being a bit low for debris, people driving into it.
That's
a few other
awesome,
things. There was
guys.
a question in there that came in. Jonathan, do you like the one on the left of the last slide? Sorry, I've
Okay, let's just jump back.
there. The last slide. Ooh.
Yeah, I don't love the one on the left of the last slide. It's got a few interesting things going on there, particularly I'd say it's at a blocking level. I'm concerned about these arrangements. It's quite thin. There's a few other issues that I'll be touching on very shortly, though, so I might continue that discussion as we move forward. But yeah, great to see people actively interested in these images and providing these comments. Whoever said, so there are some key issues here, and we've touched on all of them in those comments. That's fantastic. That means I can speed up and say, yes, this is a system that's blocked. I'm not using this slide to talk about that. What I'm actually talking about is the tire marks here that very well illustrate that this system is a situation where it's on the edge of a traffic lane, 450 millimeters wide, because I measured this. An average passenger vehicle has a tire around about 200 millimeters wide. And this illustrates perfectly a wheel snagging issue. And you can see there's several tire marks here. And by wheel snagging, I mean that someone may be approaching the system and may, with their front or even rear tires, have a tire slotting in here and hitting the system itself. And that means that we might have potential road safety issues of loss of control and things like that. Or we've got maintenance issues, and that maintenance issue I'm referring to is actually damage to our system. I mean, a tire may hit this grate and break the concrete curb or lift the grate itself. Lifting of the grate could cause some additional issues of potentially other tripping hazards or safety hazards for path users. So I'm going to ask the question of how could we have reduced this issue, but I'm also going to answer it for you. So don't bother jumping into the chat. I'm just going to move forward and say, how can we solve this issue? So maybe we don't want a tire in here after all. And there's a couple of options that we could look at, but one of them I really like and the others I'm just a little bit iffy on. So let's look at the one I'm a little bit iffy on. It's reducing the system width. And it's very similar to the image on the left of a few slides back now, but this is part of what I didn't like about that slide earlier, and that it's a reduced system width. So this is now getting very thin. This is the perfect example of a reduced system width because I've never seen one thinner than this. I'm not even sure how wide that grate would be here, but it's very, very thin. And that means that we've got a couple of things. We've got significantly reduced capacity for our system. So this drainage here, I mean, not only is it going to be more likely to be blocked, but you're also having situations where the width of the flows approaching this are going to bulk up in heavier storm events. And it may not operate so well and may even cause water to pond out into the pavement a bit more than we'd like. So that situation there, I mean, I would be sure, because this photo was taken quite some time ago, I'd be sure that this is blocked now or it's needed to be maintained regularly. Moving on to something that I love to see though, is this arrangement here. And unlike the initial images I was showing where the tire marks were there, and this is sitting sort of in a traffic lane that vehicles have to avoid by just not driving there. This is physically assisting us because what this is doing is it's set back from the line of curb. And you can see here, it's illustrated perfectly by the way that this then returns back towards the curb line. And that then means that our system, for anyone tracking along the curb line itself, this is actually now pushed away from that. So it makes it, particularly in this example, where you can see some cyclist line marking in the distance up here. That's fantastic for cyclists too, and almost critical for cyclist safety. It also gives us a nice construction situation. So it means that we've got the liner curb here, and our liner curb continues straight along here, and it makes it very easy to construct. And we don't need to notch our solution out into pavement so that we've got an area such as this that can support our grate. So if our line of curb were to continue through, you still need some grate support, and that means you actually are cutting out a small, say about 100 to 150 millimeter wide section of pavement here, just to get our graded system to work. So this is easy to construct. I like it a lot. And unfortunately, I've tried to adopt this solution in a couple of projects where I wasn't able to make it work. And the results and the reasons for that are things like my least, so as we all know from last week, like my least favorite or most enjoyable challenge, which is services and things like that. And it's not just services, it might be tree roots, etc. There's a whole range of reasons why excavation may be a problem behind curb and channel. What do you think of this system, Ken?
Oh, I like it. The question came in as to where it is. Do you know where that one is? Or
this is up in Essendon, actually, and I didn't design this, and I love it though. And it's got some issues that unfortunately we'll be talking about, but I would love to meet the designer and say good work, because I've been promoting this situation for a long time if we are required to consider a graded system.
Yeah. Thank you. There was another question from something that had come back in earlier around where handrails are needed and those sort of things. Because one of the gutter bridges had some handrails, which was one down in Abbotsford. I know that one. That may have been more around a cyclist grab rail rather than
I think so.
stop drop-offs or anything like that, because they're pretty low.
Yeah, that's my understanding of that image too. And there's actually an image in day one that had a similar arrangement. And that's in situations where a bicycle path may be linked into what's actually a wombat crossing with the zebra line markings. Well, the road rules would require cyclists to dismount for a wombat crossing, so not a shared path priority crossing. That's Victoria. The scenario, yeah. And whether or not they do, not sure.
Probably everywhere, actually. Yeah. Interesting question. Let's keep going.
Okay, great, guys. So let's move along. I'd also just like to quickly touch on another option that may be there, and this is a really interesting solution. I haven't seen a lot of these, but it's good in its intent, certainly. And what we have is an opening here that sort of connects through to a system that flows way behind curb. And unlike even this arrangement, which still has an opening that is exposed, this arrangement completely removes the wheel snagging issue for vehicles, because there's no longer the system along the traffic lane. And the intent here is that water flows in. This is still a continuous curb to curb flow system. And the intent is that water inlets comes through and outlets at the other end. You can see here, though, that over here, and I've done it on both sides of the road, sorry, that's why I've got the image in the middle here. But over here, you can see this building up with debris, and that sort of touches on probably the key issue for these systems and why they present challenges for us. And that is my favorite number one solution that I'm very pleased to see. I mean, when you have a closer look at this, you can see that some of the debris is building up in here. And when you zoom in even more, it's actually quite a lot of debris. And that this system that I love so much, it is months away from being blocked and starting to become dysfunctional. And then when I jump to the next one, you've got your smoking coffee drinkers also in this area. And we're filling this system up now with debris from just leaf litter as well, not just trash that people can put in the bin. And this system's now dysfunctional. And this one, again, I mean, this is filled up with litter. And again, this situation, this one's blocked up. And the question is, did I just show you every single one of these gutter bridge solutions or box drain solutions that they're blocked? And the answer is yes, they were. And it really wasn't hard to find these examples. And it's the unfortunate outcome of these systems, is that they are really prone to blocking. And rather than just leaving you there with they're prone to blocking, watch out, I'm just going to help illustrate why that is, so that you can understand that whilst they may be a drainage solution for your project, they have these issues, and that they may not be an ideal drainage solution if there are alternatives out there that you may consider. So why are they so prone to blocking? Well, as an example, Victorian Department of Transport and Planning has a minimum height of a standard stormwater box culvert, so the ones that are underground for our stormwater networks. And that height is minimum is 300 millimeters. And the reason for that is because after lots of testing, the decision and understanding is that less than 300 millimeters height in your box culvert, they're prone to block. And we don't want to spend a lot of time out there unblocking systems, particularly underground. I mean, that's an issue. But 300 millimeters is the go-to height for low maintenance systems. Then when we have a look at a typical gutter bridge, for instance, though, here, a gutter bridge on, say, SM curb, you might be wondering why I've got SM3. It's because it's the flattest curb profile, and it's roughly what you'd be transitioning to. It could be SM2 still, but for this example, an SM curb arrangement with 125 millimeters high, you might have only 90 millimeters height left. I mean, that's a lot less than 300 millimeters. Then on the right here, I've got our B-type curves, which you might also have in your project. And it's a little bit more, but still only 115 millimeters, around about, depends on your grade widths again. So you can see that these systems for gutter bridges, it's significantly less than our we don't want it to block height, and that these may be prone to blocking. When you then look at not gutter bridges, but installing graded trenches at 100 millimeter height ramps, for instance, we could have only 65 millimeters in height left. And that's prone to blocking. I mean, that's something that you will be out there looking at leaves and debris, filling it up quite quickly, unfortunately. And then we, of course, know from anyone who's had a look at the preceding course in the learning management system, or who attended, or who's just familiar with these systems in general, is that they're not all 100 millimeters high. And if this was a bus route, or if this were a heavy vehicle route that warranted having a 75 millimeter high raised platform, well, you might be left with 40 millimeters after you put your grate in there. And that is dysfunctional. And that's actually what we're looking at here, is about 40 millimeters high. And this system is going to be a burden for the local council in the Brunswick area. So that's a key thing to keep in mind. You can, just jumping back to this as an example, there are arrangements where, sure, you could, in certain longitudinal grades for your projects, you might be able to get a deeper system to work. So I might be able to grade down and get closer to your 300 millimeters. Maybe 200, maybe 250, maybe even the full 300 you grade into and make the system work. Well, in that scenario, though, that brings me to the other issue that these systems present, and that is through some relatively clunky animation that I prepared for this, is our foot flying and kicking and smacking into the side, and that is that, yes, these present tripping hazards as well. We are typically, and in the context of using a raised safety platform as a crossing location, I mean, we are encouraging foot traffic near these systems. And if Desire Lines took someone not immediately straight down the path, but sort of across at angles, then you might find scenarios in which these do present serious tripping hazards for us. Tripping near roadways or into roadways is not a great outcome. So I'm going to chat a little bit about how to manage these and how to look at tripping hazard issues for your project. Got a couple of scenarios here. This is not for you to answer, although it is lettered in that sort of way. I'm just going to chat through each of these locations, though, just to give you some information and recommendations on how you might treat this tripping hazard issue in your projects. So let's look at option A. That's where I'm placing a graded trench or a gutter bridge against the traffic lanes at the platform itself. And for this scenario at location A, I'd suggest that you do the full width of the platform. If this was quite an extended platform, even say, so I'm presenting here pretty standard Victorian one-way crossing with 4.5 meters, just say, across the top here. If this were a bus route, you might be extending that platform length more. I'd still suggest you go the full width, because the platform looks trafficable for foot traffic. And it would be unnecessary to cut this short just for the crossing itself. The location B, I mean, it's really great from a tripping hazard perspective. This is set back behind a curb extension. And what I'm saying is that from the parking bay all the way here, you can do the full length. And from a tripping hazard perspective, that is ideal. But it's terrible in terms of maintenance. I mean, the system's this long, it'd be very unlikely to be able to flush that when you're talking about lifting all of these graded sections off to maintain the system and make it still work as a piece of drainage infrastructure. It's a great solution, though, if you were forced to consider a a box drainage style solution, it's great for your high trafficked areas. And what I mean there, for foot traffic, that is. What I mean there is your city centres, etc., where people might be attracted to crossing this location back here, and they just got to walk along the curb extension through here to that location to cross. In city centres, I'd be suggesting that this is the solution you need to consider, because it would be unnecessary to add a lot of, that's a personal or professional opinion, of course. You're open to make your own judgment on these things, but I'd be saying high foot traffic from multiple desire lines, you're going to have to look at something like this. So if this is great but high maintenance, then let's have a look at option C above, because it has way more exposure to that tripping hazard issue, but it's way better in terms of maintenance. And there are scenarios in which you consider this. I'd say, I'm just going to chat through actually. So if you were to consider this, then, well, how long should we make this? And for shared path usage, there is information. It's actually from the diagram that I presented a couple of days ago about clearances. And that's, let's say the minimum clearance is 500 millimetres extended from each side. And if you recall that diagram, and I haven't listed it here, but desirable, it's 1 metre beyond the edge here. So you can consider those additional extensions. Again, for if it was just a wombat crossing such as this, there's no actual requirement to extend it across, but I think it's a little bit unnecessary to not extend it beyond the path edge at all. So I'd suggest that a minimum of 500 millimetres again is how far you'll be extending these beyond the edge of the path. So moving along, that's our gutter bridges and box drainage summary coming right up. Sorry, that's just talking about the demand here. And apologies, I will just jump on that. So why would you consider this with the drainage, with the tripping hazard issues? Well, our lower residential areas with lower angles for our desire lines, etc., this might suit that arrangement. So, so there are scenarios in which you look at both C and B as appropriate for your project. Okay, moving on to the summary just quickly, and then we'll be discussing ramp crossings in terms of drainage. We're coming pretty close to time for a break. Ken, is that how we're feeling?
Yeah, I've got a couple of questions for you.
Oh, sure, absolutely, please.
So is there a sloped drainage grate treatment option?
A sloped drainage grate
treatment option.
Not entirely sure what's being referred to there. I might need to take that on notice.
Yeah, give us a bit more detail of what you're thinking there, Michael. There was some discussion about removing grates for maintenance.
Yes.
And the ability to do that, which you sort of covered there, that you can.
That's right there. Grates, yeah, grates can be removable. If you're using more standard box culvert style arrangements, then they might be harder to remove as well, though. So you can also have grates that are lockable, so they're not able to be stolen, etc. There's various proprietary systems out there.
Yeah, and Pru's added in a bit more context around extending the grate as you need, and you've, I think, covered that nicely with these diagrams where you're sort of extending these sorts of things. So yeah, we will take a break shortly.
I'll just finish it. Yeah, I'll jump into the last section of drainage. It's a short little moment there. So let's have a quick. Happy to move along there, Ken?
Yes.
Yeah, great. Okay, so let's just chat about ramped crossings now, and that's from again an image that we presented in day 1, and that is our situation where our raised crossing may be connecting and ramping back down to our existing curb lines. For this moment here, I'm just going to be talking about these systems in terms of drainage. I will be delving into the mysterious complexities of actually designing these at a geometric level shortly after the break. But what I'm talking about here is it's a great cheap system because it is low impact, it's low cost, but what it also is doing is it just enables curb flows to operate as they currently were. And in a scenario where your curb is working nicely, that means this still works pretty nicely at a drainage level. And in terms of the maintenance burden, I mean, I can see a bit of leaf litter here built up, but I don't think it's heavily influenced by the presence of the raised safety platform. And that these are fairly low maintenance because it's actually sweepable, and heavy flows of water would actually generally flush these out clean. They may slightly restrict our curb flows though. So in terms of width of flow in our curb, it might just be bulking out a little bit, but again, nowhere near as much as the average thin, or at least a thin box drainage solution. So that's all I'm going to touch on for the ramped crossings in terms of drainage today. I do think they operate really well at a drainage level, and I'll be chatting about some of the challenges that these present for our project shortly. Let's move into the summary. I'll just leave this up for a few moments. I've highlighted in red that yes, I'll be talking about some other things shortly. And I think it is time for our break. So fantastic. Thanks. Let's move on to the title screen for the next section.
Okay, well, there's been some comments in there around, well, what you popped up there, the example there from they call it sort of Caulfield area, which you're going to talk a bit more about the going down and back up and how that works.
Yes.
Am I right? Yeah.
Yes,
yeah.
Absolutely. That's one of the key challenges here.
Yeah. So that's good. And I think that covers off most of what we've got there. There's a few people talking about trash grades and some examples coming in. So I think we're pretty good to take our short break. Let's take 4 minutes. We'll come back in 4 minutes, and Jonathan will kick off more with geometric design.
Fantastic. Yep. See you all soon.
Okay, we'll get back into it in a second. Just a slide came in, a question came in around the possibility of vertical trash grates redirecting the debris to a location where a street sweeper could collect it. An interesting concept.
Is okay. I mean, I like the idea of innovative solutions, and I wouldn't say that doesn't work in principle. Yeah, it's an interesting idea.
Yeah. I can't think of where I've seen something like that, but yeah.
I mean, potentially.
All right. Well, let's get back into it and keep the questions coming in. Some of them I sort of let go because I know Jonathan's going to be talking about them, or I'll collect a few and then I ask them. But yeah, feel free to use either the chat or the Q&A. And any we don't get to, we'll be able to dig into. I've still got the RRPMs. I will give a prize if everybody can point me at any documentation as to where you use RRPMs on the approach to a raised crossing, or you don't use it, because but carry on, Jonathan. Talk to us about geometric design.
Okay, great. Yes, and I guess even just touching on that question that came in there, Ken, of saying, could you consider this an alternative drainage solution? I mean, that summary and the drainage section that we've just discussed through, I wouldn't say that is the limit of drainage options for your projects. It's just a summary of some of the common things that you may be encountering. Please use your own jurisdictional standard drawings, etc. There may be other options available to you, and certainly be innovative and consider alternatives to even your standard arrangements that may solve may solve an issue within the context of your project. So geometric design solutions, no, this is the wonderful world that I live in, as well as the drainage, but geometric design is my passion, I guess you could say. I'm looking forward to presenting through this section. So moving into it, we have just a bit of a recap here from Module 1 and the principles course available in the learning management system. We have geometric principles, and that's things such as our ramp grades and lengths, our platform heights and platform lengths. We've discussed also in the principles course the principles around, is it one-way or two-way operation? You might be able to relax the one ramp for the departure side, etc. So that's the fundamental geometrics of the platform itself. But in Module 1, we started to also talk about the road environment and talk about our crossfall. And is our crossfall great, or is it too shallow or too steep, etc. And our longitudinal grades as well. And these are the sort of key components of what the road is doing for our platform itself. Is our longitudinal grades too shallow or too steep? And through that discussion in Module 1, what I'm really saying is, when a given site is within acceptable limits, those limits that we discussed in day 1, well, then our raised safety platform the design of it may be relatively simple, and that's great. I'm also saying that when it's not within those acceptable limits, it's not like the system is broken and we can't do our project. What I'm saying is that the design process may be relatively complex. And I guess eventually there may be scenarios in which it's not a feasible outcome if it's extremely beyond acceptable limits. So that's nice to know, and I won't leave it there, because really relatively simple and relatively complex is relatively meaningless unless I go into the details of it. So what I'd like to do is just jump into simple solutions, just so we can build an understanding of what I'm saying when I'm talking about a simple arrangement. So I won't be going into the platform lengths and ramp lengths, etc. That is covered in really great detail in the principles course. But in terms of the road outcomes, if cross-sectional design, I mean, I might actually pose to you guys the question here. So here's our cross-sectional design. We've got traffic lane widths, we've got some crossfalls, etc. And even before we go into our crossfalls, I'm going to ask you for a little poll here, Ken, if you could jump in, organise that. How do we want to do our race safety platform that crosses from one roadside to the other? Do we want it to be nice and straight and nice and smooth for our path operators?
Okay, so Paul's
Option
popped
A.
up on your screen there, and you're getting the option of
Nice and smooth, straight across, great for our path users, or a little bit lumpy bumpy and having the crown matched in here.
Oh, okay, sorry.
Option B.
Yeah, A is the middle one there. B is the bottom one, or you can go neither or both.
Yeah.
Right. I like it. I was looking
Yeah.
for yep. And okay, people are starting to put their votes in. We'll give it a couple more seconds. Having some I'm laughing at a few of Anthony's points that have been popped into the chat, as I'm sure others are. Very entertaining. Okay, 5, 4, 3, 2, 1. Remember, you're not marked on any of the slide stuff. Let's have a look at the results. Most people going B on that one.
Yeah, great. And we've got a few in A, got a few in both, and that's good. I'd say in terms of simple and ideal outcomes, and sorry, there were incorrect scenarios here. Couldn't have been every single one of those options, I guess. But for our scenario, the answer is, if this would just wake up again, the answer is, yeah, it's B. And I won't leave you with that. I'm not going to say, just keep in mind that option B works. I'm just going to chat through why that is. So let's have a look at option A, where I sort of alluded that it could be great by tricking you with discussions of smooth paths and etc. But the truth is that this is a pretty poor outcome because it's actually only 14 millimeters high at the crown in this exact drafted example. Once we've got 100 millimeters over here, that 14 millimeters is poor vertical deflection. They even may operate quite poorly because what might occur is that a vehicle may decide to travel towards the center of the carriageway to go over less height so they can hit it faster. I mean, that's the opposite of how we want our systems to operate. So not just crossing into the opposing lane, but also being able to travel over our speed reduction system faster. Then we will look at option B, though. It's just consistently 100 millimeters. And that's how we want these systems to operate. That means that a vehicle isn't encouraged to track differently. I do not drive like this. Hope you don't either, but some people certainly do. This is 100 millimeters high consistently, and that means that it has the correct operation no matter where you are. And it feels the same, and it's safe and easy to traverse as well. So now let's move on from that arrangement. And I guess the key takeaway is, yes, you match the crown, you want a constant lift. Let's talk a little bit now about longitudinal design. Again, I'm going to pop up another quiz for us because it's nice to get involved. And I felt like at the start of this module actually might have been a bit void of those quiz moments. So I'll keep that in mind for next time. Option A or option B, which of these longitudinal grade scenarios do we think presents the simple solution that I'm hoping for? And if that quiz has popped up in the way, just feel free to move it out of the way.
Okay, so, people pop that in. There was a bit of discussion in there around the crossfall, and if it was a one-way crossfall, I would assume that's sort of a super elevated road.
Yeah. So, and it's the same principle applies. So if the crossfall were in the acceptable level, say around 3%, something like that, then the constant 100 millimeters lift is still what we're aiming for. So you certainly don't create a crown if there's not one there, but that's when you would have a straight across from one side to the other, which means that the 100 millimeters is achieved consistently across the carriageway width.
Yeah. And Anthony's popping in some stuff around the specific context, and if you have some non-compliant or some odd crossfalls to be adjusting. And I think that's really sort of hitting the nail on the head of context-sensitive design and adjusting as you need.
Absolutely. And look, and we'll be going further into that today. And those examples, including the examples that we're about to run through for longitudinal design, we're talking about ideally it would be like this. There's, of course, context-sensitive adjustments that are required.
All right,
So
let's
that's
end
the
that
poll day.
poll and share the results and get lots of votes for A on that one.
That's great. People have, most people, and I do apologize again for any confusion or tricking, because there's right and wrong answers there again, but the majority of people got A correct. B's a little bit steep, and I'll just chat through again without leaving you with mysterious answers. I'll chat through why that is the case. So the answer is A. Sorry, we already talked about that. So option A, let's just have a look at why it's good. And reflecting on what we learnt in module 1, we have 3% longitudinal grade. I mean, that's great for our heavy vehicle acceleration. Not that we necessarily have them here, but it's good for acceleration. We've also got our path crossing crossfall is in that acceptable range for DDA. So sure, I'd love this to have been 2.5%, but it's less than that 3.3% that we were discussing. And I haven't even highlighted it here, but this is our desirable grade for deceleration as well. So this is just ticking the boxes for a site that is going to work well without needing to do too much extra work. Then we have a look at option B. We've got not a lot of boxes being ticked for this being a simple project. So we have some situations where we've got poor acceleration for our heavy vehicles here. We've got a crossing crossfall that's too steep, so we need to look into modifying that. That's way too steep if this were to comply with DDA compliance requirements. And then we've got a maximum grade for deceleration. This is hitting our maximum grade. So there's not a lot of things I love about this for just popping in a simple design solution. Some of you might have picked up or been thinking about this being level, and yes, I mean, this may not flow, so this could even hold some water on the ramp. This being steep, not really an issue for me, because and I'll chat about that shortly as well. So sites that work well, sites that don't work well, but may still be able to be resolved. Here's another quiz, because we are rolling through the lessons through interaction here. What we also have is a question about where should we now measure our platform height? I'm talking so much about 100 millimeters high platforms and occasionally referring to our 75 millimeters, but let's get back in here. This is to illustrate it as well, sorry. We've got at the top, from the toe to the top of the ramp, such as I've illustrated here with A. And I've also got my poles in the way there, that's okay, but got option B here, which is directly and vertically below the top of the ramp. And no, neither or both, because it's only one or the other.
Okay. All right. Well, we'll give it a second for people to pop that in. Yeah, so we're going to start to chat a little bit around shortly around how you can adjust things if you've got these situations, which
That's correct,
yeah. I'm quite interested in. But we'll give it a second here. Yeah, people are pretty good on the polls. They're pretty quick, and they're a good way to ensure people are thinking about this. And, you know, they're a good little practice for your actual quiz after the session as well, aren't they?
That's right. Yeah.
Yeah. All right. Okay. And let's end that poll now and share the results there. We've got most people on B there. A few in their head and thinking A might be the possibility. Back to you, Jonathan.
That's great. Okay, thanks for your involvement there, guys. And it's a little bit trickier there. And the answer is B, this one here. And A, it seems attractive to think, because how would you measure it otherwise, especially one that's being constructed? You can't magically measure vertically below anymore. But the truth is that it is measured like B. I'll just chat through again why. So if we were to have, when we're measuring vertically below to a projected road surface, this allows the whole system to have consistent ramp angles, and by consistent ramp angles, etc. What I'm talking about really is, in this scenario, we've got 3 and 2 is 5, and 3 and 8 is 5 again, with the 8 minus the 3. And actually, it's a great opportunity now, Ken, just to also mention that I'm regularly using 5% in all of my examples, because it's mathematically easy to present to you all. It doesn't use decimal places, etc. Please don't be thinking that your speed environment always works perfectly for 5%. It's discussed in the principles course in the learning management system, the scenarios in which you use different ramp rates. But for today's presentation, I focus on 5% because it's a lot easier for me and potentially easier for you to understand.
points come in, and I think it's a decent one from Ryan. Should it be perpendicular to the slope of the road, which I think it actually should be. Your blue lines sort of at that point, it should be that. It's going to make stuff all difference, but I think that is right, isn't it?
That's a good question. I'm going to have to double check the geometrics of it.
The reason I say that is basically you just take your road and you make it horizontal, and it would stick straight up.
Sorry, correct. Yes, no, that is correct. Absolutely.
We can tweak that a little bit.
Good. No, that's
Ryan can have a prize for super eye for detail.
I think that is brilliant. Thanks. So let's just move along to what we then have. We have a situation on the right-hand side for the trickier options for measuring from toe to top. And I'm going to use a 5% example because, again, this works really easily for us here. And when we lift our top, so when we measure from toe to top, in this scenario it's 5%. Well, if we did that, then we'd have a 10% ramp. And if we were to do from toe to top, well, that's actually 5%. It hasn't changed the grade here. So that's a 0% increase. So there's no ramp here all of a sudden. And then if we grade between those two, then it just doesn't make any sense anymore. We've turned out 5% into a 9.4% platform. That doesn't really operate correctly, and we've worsened the platform grade. So hopefully that helps illustrate the challenge or the issue if you were to measure from toe to top, and that it is actually a projected measurement. And again, what I'm talking about here, and this reflects back on that comment that was made about where are we measuring this from. But what we're going to look at is just what a simple site may do. So if our crossfall and a longitudinal grade is operating correctly, then what I've got here is some, just sitting on the plane here, I've got the toe of the ramp and the top of the platform here, and the blue dots and the toe of the ramp again in red. And what I'm saying is that a simple design is as simple as grabbing your platform and just lifting it up to create our race safety platform. Because when we do that, our crossfall's correct for the path users, and the longitudinal grades are acceptable. It's as simple as that. That is your project. That is the fundamental platform design solution working as it should. Really great, simple outcome. And many of you may find that this is exactly how your sites work. By simple, I also mean simple design processes. So if you are out there and you've validated your sites and you're looking at them and saying, hey, wait a second, we've got perfect crossfall for this project and the right longitudinal grades of our road, and it's not too wide and everything looks like it could work here, then you might not need a very complicated design. And even a 2D design solution may work here with just the instructional information for how to construct it, and that we're raising it by 100 millimeters, etc. In more complex design solutions, where you might need to regrade roads, etc., or you might need a full detailed design of this platform, though, to make sure that we're actually able to construct it correctly. So moving into complex designs, and this is where things get a little bit trickier for us, is when our site didn't work how we wanted it to, and we've validated our site and we said, oh, wait a second, this is not within the realm of a simple solution. We're going to have to change our longitudinal grade or our cross section to make this project work. That's when things get a bit trickier, but most of the time we can resolve these issues. And occasionally, as I've discussed and mentioned, you might end up with a feasibility issue though for a site, and you might need to re-strategize your solutions or your path networks if you cannot get a site to work. But it is rarer. It just often depends on how much money you have to spend to solve the solution, to be honest. Let's use this as a cross-sectional example of a complex site. So when I say complex for this site, we might be able to make these 4.5% crossfalls and these 5% crossfalls work in terms of crossing grades, etc. But for the hypothetical world that I'm creating here for us all, let's just say that this has overturning issues though. So this is near an intersection, and that these grades and the longitudinal grade of the road combine to cause a truck overturning issue, such as what we were discussing in module 1. And that, let's talk in the context of a little client designer interaction here, and we'll say that the design engineer and the client, we've worked out that the target crossfall is 3%. Okay, so no longer 5%, 4.5%, 3% crowned is what we're aiming for. So again, I'll ask you a little bit of a question here. If you could just perhaps just pop into the chat window just quickly. I'll give us a few seconds here. But do we want to lift up our crown, lift up from the crown and change the curb on the outside, or do we want to keep the curb and cut down? I mean, what do we think the right sort of solution here may be for us, and what is preferred? Any thoughts?
Okay, so do we go up or down? Really, are the
Basically, yeah.
are the choices? And yep, people are wanting to go up generally. People want to go up.
That's great. And I'll jump in there and already just discuss that. Yes, and going up is a great outcome, and typically means that you're not doing pavement reconstruction. So for this option here in the magenta purple color below, we're cutting into pavement. We're losing pavement strength and probably actually requiring pavement reconstruction for any major crosswall changes such as this. And that might be an expensive outcome as opposed to lifting up and reconstructing a bit of curb. It might be cheaper for us. But the truth is that, for your site, there are scenarios in which you consider both, and either option may suit your project. I'll be chatting a bit about that shortly, and I might even highlight some of the key issues for why you might have preferred to do the cut down option. But so for our example, let's say the client has agreed and we're happy to lift the carriageway up to get that desired 3% crossfall. So what I'm talking about here is that we're keeping our crown and we're lifting up these points, and that gives us sort of no change at the middle. We maybe have cut in some asphalt to do some asphalt work over here, might have a 40 mil overlay still, but the levels haven't changed. Then we've got 50 mils at the edge of our traffic lane and 91 at the lip of curb is how the maths works for this example. Just for anyone wondering, what I'm talking about here at this cross section is this is at the toe of the ramp. This is not our platform. This is correcting to the 3% that we're looking for at the toe of the ramp, and then our platform, of course, is lifted up that matches that 3% as well. So the client's happy with this. We're all very pleased. And then all of a sudden they said, wait a second, I thought this was going to be a lump of asphalt on a road, and I've done my budget, but I haven't quite finished it. And I'm concerned about how much pavement work is now involved though. So how much pavement work do I need? I mean, over what length am I doing this? Let's just jump into that and discuss how we change from one cross-section, one crossfall to another. And it is, a joke to Ken and the Safe System crew there, is that it is the single coolest word in road design. We are a boring bunch normally, but we've got super elevation development. I'm so glad we don't say camber anymore in Australia, because we get to say a fun word like super elevation to our family after a long day at work. It's also got some cool illustrations in here from the 70s. I'm sure all engineers still look roughly the same, but they've got these great images as well. So it's a fun part for me in my daily job. So let's just say that super elevation development, well, again, I'm not going to leave you in the mysteries of what that word means and leave you to look it up. I'm just going to run through an example of how to calculate for this example a super elevation development from one crossfall to another to solve our issue for that site. There's various ways that you can calculate super elevation development to change from one crossfall to another. I was going to go into them and I realized that it's less meaningful than just referring you to the great summary table, which covers off both rate of rotation and relative grade methodologies for calculating this stuff. That's some nerdy language. Don't worry about it. If you really want to look it up, have a look into Austroads Guide to Road Design Part 3. So what I'm going to do now is not just leave you with this table as well. It's a bit of a tricky table to get your head around it. Any road designers here know how to use this already, but for your planning of your projects, it's handy to actually get your head around this too, so that you can understand if you were to be changing crossfall, what these lengths may be. So on the left-hand side, we've got operating speed. We've then got number of lanes. So I'm going to use this example here, which is a 3% to 3% crossfall change. Number of lanes, typically it would be a single lane twist for a crown carriageway. If you had one-way crossfall, you might be tilting it from one edge only. You could be looking at a two-lane twist though. And then we've got our crossfall change, which I suggested just earlier, is from 3% to 3%. So that's a 6% change in crossfall. And then we've got the development lengths required for our speeds and combinations of lanes within the crossfall changes. So there's also guidance here. I've got some of the notes for this table not shown on the screen, but it also recommends that you round these up to the nearest 5 meters. I think for low speed environments, etc., that's slightly less important, to be honest, but for cost estimating, it's pretty handy to just consider rounding each of these values up. So now let's take this to our exact example. So I've just cut it off at the crown because it is a single lane sort of side of things. But you may be asking, well, is it single lane or we've got a parking bay too? And for whatever reason, we're not doing curb extensions here. We're just going to twist, we're going to get this whole thing corrected to 3%. And the question is answered by saying that's either in principle. So I don't really mind if we, I'm talking the wrong thing there, I jumped ahead. It's going back. Should we be using our operator here in the next slide? Amazing, I see the future. Typical road operating speed or decelerated speed. So when we're approaching these platforms, should we be using our operating speed for our road, or should we be assuming that our vehicle's decelerating because they can see the road safety platform? And I'd say, yeah, you can consider either operating speed. But really, I'd be saying that I'd use the operating speed because it's lower risk. Assuming that someone's decelerating for these systems is an assumption. You might not know how fast they're decelerating, and we might as well make these as comfortable as possible, or at least as a starting point or in planning. So for our example, let's use 50 kilometers per hour. And now let's have a look in here and talk about number of lanes, which I've already jumped into and spoil any surprises for us. So do we have a single lane or 2 lanes because we're using parking bays? How many lanes should we consider the site to be? And the answer is 1. I mean, it's a crown carriageway. We're only going to be looking at 1. And the principles of super elevation development, how fast you're doing it, is more about for vehicles traveling, right? So the parking bay doesn't have people operating at speed, traveling along, and I'm less concerned about twisting a bit quicker for this lane here. So let's say, and in that example, I'm saying I don't really mind going up the 91 millimeters for this location at the same rate as required to go up the smaller 50 millimeters here. So 1 lane rotation. And then when we see these combine from 1 lane and 50 kilometers per hour operating speed, that's 28 meters. And you might be thinking, that's huge. Oh my God, that's a lot of pavement. But again, that's over this larger 6% shift. So this table gets a little bit tricky like that. But when we try and reduce this 28 meters down to what it means for our site, we're saying that 28 divided by the 6 is 4.6 meters per percentage change in crossfall. And in our project, we've got a 1.5% change. So that's 1.5 times 4.6 is only 7 meters. And that's a big sigh of relief from our project engineers, realizing that it's not a huge shift. And then should we round this up to the nearest 5 meters? I mean, I've already discussed it. I don't think it's critical. These will still operate safely at 7 meters. That's how the math works. But I'd also suggest that we're doing cost estimating. Let's just say it's roughly 10 meters of pavement correction, of additional pavement works required for this project. And in this scenario, of course, the client is very stoked that we got that correct, and they're able to include that cost in their budget. So hopefully that helps us understand, at least at a fundamentals level, how to, for a site that wasn't getting the cross-section quite right for our desirable outcomes, how we might be able to consider the fundamental lengths that we may need to correct our crossfall over. As was really well, an excellent comment made earlier was, you also might have something that's really quite close to correct. So if this was, say, 3.5, and you still wanted it to be at 3 for our overturning issue, then you might be able to get some tweaks to the actual heights of platforms, etc., to get an acceptable outcome. You might not be talking about actually reconstructing pavement over extensive lengths. Let's bring this to the complex scenario for longitudinal grade now, though. And before I jump in too much further, actually, I'll just go back a slide so we can keep focused. Ken, was there any questions on crossfall correction there?
No, I think we're good at this stage.
Yep.
If you jump into the next one, yeah, we might have a little more discussion about it after.
Yeah, sure, mate. Great. Okay. So now let's have a look at what we've got here for our longitudinal grade that was too steep, in my opinion, at least, and for all the lessons that we've been learning. So for this one, just another quick quiz for us. If we can all just say, let's just rank, oh, sorry, going the wrong direction there. Let's rank our issues here from which direction? From worst to least bad. We've got A, where it's a bit too, so where it exceeds our maximum grade for acceleration. B, where it's too steep for the crossing crossfall. Or C, our maximum, where we're at our maximum grade for deceleration.
Okay, so the poll is up on screen there. And yeah, this is another one where you get to make some little choices. Okay, I'll give it a little bit more time as people have a ponder of that. And yeah, so it's always good to remind people that you, of course, are exaggerating things here. People
Oh, of course. Sorry, thank you for bringing that up. I've greatly exaggerated the vertical here. 5% road is not nearly 45 degrees.
So yes, that's
right.
I'm sure all of our experienced people on this course are very aware of that, but always worth reminding.
Yeah, absolutely. Great.
Okay, we'll give it 5 more seconds. People are making their choices there. 4, 3, 2, 1. I'm drawing out my seconds there. All right, let's hear the results.
Let's see how we're going.
Over to you, Jonathan.
Okay. Actually, those results just disappeared from the screen a little bit for me, but I will tell you my version of it. And you're all aware. Oh, there we go. There's a lot's thinking that we've got a B is a major concern. That's fantastic to see. I agree with that, and sort of mixed results for the others. So now I will move along and head towards what I think. And I've got here JTG says, because this isn't a strict rule. I mean, you are able to apply the right judgment for your site to understand what may be the key concerns here for us. So can you take that poll down again? It's just covering my screen now.
Yeah.
Thank you, mate. Perfect. So JTG says, I think it's BCA. And I'm saying that this, for our crossing location, this is a dysfunctional grade. I mean, we don't want our DDA users using this grade. So that's a key issue if our crossing just doesn't work as intended. And then I'm also saying that whilst A exceeds our maximum grade for acceleration is kind of a minor concern here. I mean, it's not really a major road safety issue, but being at maximum deceleration and having potential braking issues is. So I'm saying that system doesn't work well. That's a major problem for our project. Braking challenges, that's a safety issue and a bit of operational concern for A. So let's move along and just talk about these primary concerns, our secondary concerns, our minor concerns. But actually, before I solve these issues, let's just have another look at ideal race safety platform longitudinally. So what we have here is, this is ideals. You will never find ideals in the real world, but this is what the system and the math and this is what we'd love to have. And you may be able to construct something that's, within millimeters of perfect as well for these scenarios. So I want all these grades to be the same for ideal operation. You might not find it, but that would be great. If you're on a vertical curve, it's already getting impossible. But on a straight section, maybe that's how these could operate. I'm also saying that therefore, all of these angles for this geometrically to work are the same. So A, B, C, and D are all equal in an ideal world. And that all these principles here, they don't change depending on the grade we're at. So if we are on 1% grade, then we've got our 4 and 1 and 5%, then our 1 and 6, 5%, and our 1%, 1%, 1%, and all our angles remain the same. So that's what we're sort of wanting here, right? And I'm bringing this up because as soon as we start to look at our grade is too steep, then we start to realize that achieving this could be costly. It still may be possible, but you might need to also start to compromise in some of these arrangements of what the ideal solution would have been. Let's have a look at now our issue, and we'll say we've got a primary concern here, and we'll talk about some of these as we run through. But what we've got is our primary concern is the system. We need to get this flatter, so something like 2.5% or perhaps 3% might be acceptable. I'm wondering, how should we change this, modify this platform grade to get what we want to work? And I'm going to now pose to you yet another fantastic poll. Hopefully there's not too many now, but this would be great just to get your opinions again on this. I'm going to say, do we want to resolve, just going back again, to resolve this steep grade issue, do we want to regrade the whole road? Do we want to change, without changing the ramp angles, and getting still that 5% change, which is helping us decelerate the right speeds? Do we want to kick off our magenta option away from the blue steep option? So we want to get 3% here, but just lengthen our ramp. Well, maybe we want to keep our ramp absolutely fixed in terms of its dimensions, so same ramp lengths, but just modify the levels and tweak around with that within the same same footprint. Or do we want various combinations of D, or is the mysterious it depends scenario flying in here as well? So can we just get a feel from you all? Another quick poll here, perhaps timing's not too bad, Cam, but it'll be good to roll through this.
Yeah. No, it's popped up on the screen there. And while that comes in, Prue's popped a good question in. Yep. Would you say installing a raised crossing provides an opportunity to address the crossfall issue at an existing crossing, as opposed to an untreated crossing, which will always retain the longitudinal gradient of the road?
Yeah, it does. Yeah. And I guess in a similar way that you can resolve grading issues for a raised crossing, you can, consider minor regrading of path areas or crossing areas without a race safety platform there. But that's quite extensive work. And if a race safety platform would be appropriate, then yeah, certainly gives you that additional opportunity. It's a great pickup, actually. Good comment.
Okay, people are nicely filling out this poll, how to fix longitudinal grade. And we're going to end that poll now.
Okay.
And we'll have a look at the results. The most popular one there is it depends.
Yep, and that's great. And there's also a good mix through there. And I'm sure that the other comments in there are based on sites that you're familiar with or the assumptions that we can draw. And the truth is that they all are pretty good, and that it does depend on the scenario. And even something that I've drafted this and looks a little bit odd here, but even this is a reasonable scenario as well. So rather than leaving you with all that, I might just talk through why, just with some examples. It doesn't necessarily cover every scenario, why these may work well, but why would we consider them? And something like option A, where we're regrading the carriageway, has the best opportunity of creating that ideal outcome that I was talking about earlier. So you could regrade to approach this at, say, 3%, and then have a 3% platform and a 3% departure grade. And that might be great, but it's kind of expensive because there's a lot of pavement works involved. It could suit a new road though. So a new road in an environment where you're realizing that, you were having the idea you might have a new road that's a bit steeper than we wanted. Well, certainly then investigate regrading these to be perfect. But it could also suit a major rehabilitation project. We've then got options like B. So this looks a little bit odd again, but look, this can work just fine. It's for smaller grade corrections. I'd suggest A is for your larger grade corrections. But option B could work really well for that scenario. And it's actually okay. I've used these a couple of times in your entrances to, say, service stations, etc., which already have a sort of layback environment for the access to these service stations and the path coming across the front. I'm not saying that you have to use them at service stations, but I have found that to be an appropriate location to adopt this. And it's actually quite a small change to the roadside to get something like this to work sometimes. Then option C, I'd say it's for tiny changes, but why make your ramps longer and why regrade anything if you can get an acceptable outcome from very small changes in carriageway levels? So things like your 3.5 to 3% longitudinal grade changes. You could draft this and it could be just a little bit lower at this end as a ramp height. It could be a little bit higher at this end as a ramp height, and it just works though fine for your site. And of course, D, I'd suggest you might as well be doing A if you're doing some serious work, but sometimes you're just stuck and you have some really complex, say, conflicts here. That means you have to start and kick off at a new angle with some of these principles applied, and then you're doing your regrading anyway. So yes, they can all have their merits and they can all be useful. Now let's just use, just as a quick example, I'm just going to run through one example of regrading, just for your awareness, and it might, and hopefully it will highlight a couple of opportunities for you and your projects in understanding what criteria might be acceptable as well for regrading. So I've added a little thing in here. It's construction effort. I've got some site distance concerns and acceleration that we'll chat through. But let's start with construction effort. And I'll say for this example, I'm going to use tiny value curves. For any road design enthusiasts out there today, you'll understand that K values represent how sharp a curve basically is, whether it's a sag curve or a crest curve. And that K value of 2 is pretty small, and that it would have, in extended long curves, would have sight distance concerns. And also that to achieve desirable, say, approach sight distance, you need a curve much bigger than K value of 2. And for the nerds out there, it's 13.8 is what we'd actually be wanting for a typical approach sight distance. Let's have a chat through, though, about how this could operate. So short curves, a little bit of regrading. What's this doing for us? And it's worsened our acceleration issue. So this is a bit steeper through here. But again, that was like my minor concern. And a vehicle can still accelerate. It's just doing it a bit slower. So maybe we accept poor acceleration for our site. We've then got 250 millimeter lift here. And if we were to put this larger 13.8, this becomes significantly larger, and I actually drafted it up. I won't be presenting it today, but it's around about 600 millimeters. And that's the difference between full reconstruction over, say, 80 meters versus a relatively compact system and an overlay solution of, say, 250 millimeters lift, maybe some reconstruction, or you could have that as an asphalt overlay. And this system here, as I've drafted for this specific example, it's only 30 meters long. Sounds like more than we wanted, but really, when you remove the platform from this situation, it's only 5 meters on the approach up the top. And it's an additional 15 meters of pavement work beyond it. So it's not crazy to have resolved the grading concern here for us. And the question that's on everyone's mind should be, or hopefully is, well, how's that work that we talked about, these short K values? How's it work for our sight distance? And the truth is, it actually just does. Because these very short, sharp curves that we've adopted, around about 5 to 10 meter lengths, straight from the toe of our ramp, it actually means that we've achieved our sight distance. If you start going a little bit bigger than these, they come out at the wrong angle and start to block sight distance. But short curves actually may work for you and may be a better solution than sort of medium sight value curves. And in terms of costs, it might actually be an acceptable outcome that is superior in terms, particularly in terms of cost, to one that adopted desirable approach sight distance values from the guides. So whenever you're doing your design solutions, have a think about, don't look at conformance. Have a think about what we're trying to do. Sight distance is a distance that we're trying to see. It's not a value for a curve in the guides. And there are different ways we can achieve our sight distance that may be different to the values within the guides. So for this specific example, I think it's a pretty good outcome. I'm happy with this as an arrangement. And I'm sure if I spent more time on it, I could find some issues that I didn't like, but it's a reasonably good start to getting a solution for us. Now, let's jump into ramp crossing. So our ramp crossing has some requirements. And when I say ramp crossings, I'm talking about the scenario that we discussed earlier, where it ramps down to, say, an existing curb line or existing pedestrian crossing location. And there's some requirements for this. I mean, there's no design guidance that says, here is the section for ramp crossings. Here is where you learn about how to design ramp crossings, other than in our course, of course. But what there is requirements for how slopes and things need to operate and interact. And by that, I mean, there's an acceptable grade for how this section here would operate. And there's an acceptable or unacceptable angle combination here from one slope to another. And I'll chat very quickly about those. I'll just suggest that this is not this cross-section does not cover every condition though, so just keep that in mind. I'm just using an example with some lanes, parking bays. Your sites may differ, but it's a good enough example for what I'm going to discuss shortly. So let's have a look at what an acceptable grade here might be. And that's, again, very similar to our crossfall scenarios. It's sort of covered by Australian and New Zealand standards for ramp walkways. And by that, I mean not your pedestrian ramp, but say a ramp leading towards an overpass. What's too steep for too long, things like that. And again, from our day one requirements, it's the same. It's just saying that if this length is less than 1900 millimeters, then up to 7% might be acceptable. But if it's too long, actually, no, let's leave it at that. That's right, because I think 7% is probably the maximum grade we'd be looking at anyway. Then there's also separate requirements though for your pedestrian crossings, right? And that's saying actually, if it's over a very short distance, then we can ramp up a bit steeper. So 7% for longer transitions that are greater than 1900. Sorry, I said less than, apologies, that was an error. And then we've got over 1520 millimeters, a nice little value there from our Australian standards, can be up to 12.5%. So that's good, some values. We've also then got the angle requirement. So from, again, the Australian standards referring to DDA requirements, this might be a bit tricky to negotiate for a wheelchair. And we do have values that we can refer to, and that is saying 166 degrees. We don't want this angle to be less than that. It's a bit of a random number until you realize that that's roughly 25%. And 25% is roughly, going back over here, it's roughly 2 pedestrian crossings toe to toe. So 12.5%. 12.5%. That's the maximum grade change. So that gives us some information for how to get a conforming solution for our DDA users. And I've just made that point there. So it doesn't mean that it's ideal though for every scenario. I mean, ramp crossings, they have benefits. They are lower cost and they are reasonable drainage solutions that work quite well. But they're not ideal for, say, a shared use path. And the reason for that is that a cyclist using the shared use path at a priority crossing, such as what we're seeing here, they need to decelerate. Well, they may not need to, but a 25% grade change is pretty sudden. I'd suggest that they would need to decelerate for that arrangement. And a cyclist decelerating on approach to the crossing might give a vehicle the wrong information. The vehicle might get confused and think, wait, am I giving way to them? Or are they stopping for me? And who's going first? Confusion, as I said in day one, it's not an outcome that we want from our designs because it can lead to poor judgment, poor decision-making, and road safety concerns. And of course, it's also can just be a bit difficult and uncomfortable to negotiate. I'd say that whilst we can also, just go back a slide, whilst we can meet our Australian standards requirements for a DDA compliant situation here, I wouldn't say it's great for people with mobility issues. So just also keep that in mind, that conformance is different to an ideal outcome. But certainly there are scenarios when ramp crossings work well, and I wouldn't shy away from them. And even in this example here, where cyclists may need to decelerate, a little bit of if the ramp crossing worked well for your drainage scenario, then a little bit of extra work on rebuilding this path side to be a bit smoother might alleviate that concern.
And there were some specific comments that came in around some of the requirements there. Doesn't 1 in 14 require handrails on both sides of the ramps? And question of whether the recent standard has a maximum of 1 in 10 there. So I think you've sort of covered that.
Yeah, no, that's great. I think in terms of handrails, that's for certain scenarios and includes mobility, but yeah, that's great. And I'll be happy to touch on that later. I think I'll just keep moving through the ramp crossing section now, though. There's just a few other concerns I'd like to highlight for us, and that's arrangements such as this. So for this example, I've got 1.5 meter ramps that are conforming and meeting the requirements for whatever we needed to achieve. But we've also got some vehicles and cyclists here, and I'll just say that I'd like to highlight a few concerns. Again, it's similar to me discussing how a vehicle for the cross-sectional example earlier might choose a different path to negotiate these at effectively lower ramp heights. And again, I do not drive like this, but you can see it out there, and I hope you don't drive like this. People may choose to actually go out wide to hit the ramp a little bit faster with the less ramp height for their left wheel in this scenario. So that's not ideal. And then also a cyclist traveling along here can have serious issues in negotiating, suddenly driving along a very high crossfall. So riding along the ramp section here may lose control and crash. So we certainly don't like that as an outcome. And that's some very real, particularly the cycling issues. These do not operate well for on-road cycling either, unless there's other treatments, that is. And so, for instance, to reduce those sort of issues, then we've got something like this, which could be curb out stands to assisting in minimising exposure for the road users to actually need to try to negotiate the ramp portion. So that then, of course, requires some additional consideration for our bike users. And these additional widths, so the residual widths that are here, I'd suggest that that's exactly similar to considerations to our module 1 discussion about curb extensions and what sort of widths do we want for our laneways. So just be aware of the issues here, and that the solution also may require some consideration for on-road cycling and, of course, vehicles and various other things. So here's just a quick image. I won't spend much time on here, but here's a good little example. It's got some additional signage here, but this is a good example of this actually making road users not exposing the ramp portion to road users. So that's actually the end of our geometric portion. We've got a little bit of time left, and I'm just going to run through our pavement design principles, and I'll just introduce the lighting section. We are running pretty well with our time, but I will just jump straight in if that's okay with everybody. So pavement design, this is not going to be a pavement design course. I will mention that, I've already mentioned it earlier, I will mention it at least one more time as a reminder, but this is going to talk about some pavement design principles. And look at this truck again, I'm very, very pleased with this. This is the nicest looking truck I've seen in a long time with our JTG Road Engineering and Safe System Solutions synergy together. We've got our downward pressure that this truck is applying to our road surface here. And there's a few other forces involved. We've also got our braking forces when a vehicle is decelerating. And we've also got our sort of acceleration, our churning acceleration forces. So pavements typically are required to allow for these. And yes, it's more complex than that. And there are some other shear forces and turnings, etc. But fundamentally, let's talk about these today. As we move forward, I've cut off Ken's logo, which he will not be happy about, but I do like the truck still. Looks very nice to me, with the JTG Road Engineering logo still nice and prominent. Our downward pressure, let's have a little chat here about pavement design and just what it needs to achieve. So it's holding, typically design is about our downward pressure. And for a flexible pavement, it's something like this, where it's got a wearing course of, say, asphalt, and then a base course, and maybe various base course layers and sub-base down to our existing ground level or constructed subgrade. So that's a typical flexible pavement. And then I've got a typical rigid pavement, which may be something like concrete, sitting on a sub-base, on a subgrade, or perhaps against base course layers. And there's a million variables in the way that these systems can operate. And again, this is not a pavement design course, but we will be covering the principles that apply to a race safety platform, which is not shown in this image here. Let's just jump into a question for you all. It's just another quick quiz. I hope we have time to finish all the quizzes here, but we've got wearing surface for our flexible pavement, our base course, our sub-base layer. I'd just like to ask quickly, if we can all jump in quickly and say, how do we want to construct this? Do we want it to be like option A, where all layers are formed following our race safety platform shape? Perhaps B, where it's just a subgrade, a nice cheap pavement is making up that shape, the extra height. Is it like C, or they all might work? That image has popped up a little bit strange on my screen. Apologies if you can't see this correctly. But D is they all might work.
Okay, well, I'm not sure if we've got a quiz popping up.
That's okay. Perhaps you can just spam.
Yeah, just type it in the chat is good. What do you people think?
Just to get a little bit of a feel for it.
A lot of C's and D's coming in.
Yeah, great. That's cool. And it is that answers all our questions very nicely, because the answer is D. And the reality is, but C is really good a lot of the time.
Okay, good.
Yeah, so excellent for the C's and the D's out there. I'll just quickly chat about why that is. And it's because our flexible pavement systems rely on continuous and uniform compaction of all layers. And compacting all these layers is kind of tricky, particularly in the ramp sections. So ramps are complex to grade and construct, and they might not be of widths that are easy to grade other than and compact without hand compaction tools and things like that as well. So it's quite tricky to do. Here we've got the nice flat sub base and base layers, and that's able to get really good compaction in here. And then we still need to grade these trickier ramps here, but that's actually with our firmer asphalt that's easier to form. And I'd much rather do 2 tricky grading processes than 3 at the top. So I'd suggest that option A can be constructed. I've actually seen that in design packages that I've reviewed, and it can be done, but option C typically works pretty well for our projects. Just for the concrete pavement, again, just to spam the chat window quickly, but then understanding that and taking it for concrete pavements, how might we look at this? We've got just 2 options here. And I'd say This option 1 has the continuous concrete at the top here on the trickier subgrade, sub-base layer, or do we want to just fill in the whole thing with concrete?
There was a question while that people have a think about that. What's
Yeah,
the
sure.
minimum ramp length that can be compacted effectively?
Well, it is the minimum ramp length, and I'd say that, and even less than. So you could say around about that 1.2 meter length ramp can still be perfectly can be compacted, and even less than that can be compacted. It just changes the machinery that's used. So I like a standard 500 millimeters minimum for compaction areas because it's a good size for the larger hand compaction tools, hand vibrators.
All right. Well, we only got a few minutes left, so we've got
That's right.
actually a mix of A and B on this one, Jonathan. So let's
Yeah, that's pretty much spot on. So let's just say that it could be either. For me, I like A. A is a solution that, if this is strong enough at this thickness, well, this is thicker than it needs to be and probably more expensive than it needs to be. But this operates just fine. Don't restrict ourselves to only these thin options, but this is a typical arrangement that I'd be looking at. Just very quickly, talking about downward pressure again, it's the same whether it's on a ramp or over here. Our design is based on the same subgrade and same vehicle volumes. But we may find ourselves with a few issues such as this. So there's some issues at the toe of this ramp. And why are we looking at that? It's because as our truck arrives with its downward pressure, well, some of that weight is shifted to shear forces here. And that can cause a weak point at the toe of our ramps. So that's the approach to the ramp. And the departure of the ramp, flying trucks like the flying cars of day one may arrive here, flowing down the ramp and create additional weak points in our pavement. So these do create a weak point potentially that we need to manage. How can we manage that weak point? It may be as simple as adopting a thin asphalt. It may be as simple as our asphalt pavement design for this road already allows for that, and that it's strong enough and thick enough, and the asphalt type that we're using here is heavy duty enough to resolve that weak point. If, however, our project is smaller scale, we may be looking at a high strength asphalt here with a lower strength asphalt either side, then I'd suggest that you look at what's called a reinforcing asphalt strip with various other terms, but looking at adding and extending about you could go less than this, but 500 millimeters, as I suggested earlier, is a good compaction width for me. And my projects are like that, extending the asphalt out. So let's just have a quick look at those options here. That might be a thick asphalt pavement that just extends that 500 mils beyond the ramp toe. It could be a thinner layer on intermediate course of additional asphalt or crushed rock here to reinforce that weak point. Or it could be in the lower cost projects that are just popping a thin layer of asphalt on. Rather than any adhere, perhaps just extend your thin asphalt layer by that extra width. That will help minimize that cracking at the weak point. Just a quick comment on braking acceleration, if I can. Ken, is that all right? Or are we a bit slow on time there?
Let's quickly jump through that.
That's great. So we've got our braking forces and our accelerating forces that can occur so vehicles braking and potentially stopping and accelerating after they've given way to somebody. And then at the departure side, we've also got those acceleration forces where you start kicking off and starting to get back up to speed. These apply some forces to our pavement surface that is a bit different to your average travel conditions, and that's shear forces, and that can have almost no issues for your typical asphalt pavement design, but it can be an issue for our spray seal. And spray seal roads are relatively common in urban and rural environments, and as rural towns grow out, they may still have spray seal roads that are in areas where you're installing, for instance, a race safety platform. That may cause a serious issue where it rips up the steel, you've got maintenance issues. Just quickly rolling through, as we are getting close to the end here, as a guide to cost estimating, you might be wondering how much should you be replacing of your spray seal with a new asphalt pavement that could resolve the issue for you. And the guides tell you go the full length of acceleration, and there's nothing wrong in doing that. It's just really expensive. And I think the key forces for where this becomes a major issue are more in the last 20 to 30 kilometers per hour of deceleration. That's roughly 10 to 15 meter lengths. I would be suggesting that if you're on seal, you'll be wanting to do 10 to 15 meters at a minimum, and that if it was longer, perhaps your design vehicle length, you might be looking at that as our minimum. Okay, fantastic. Just jumping in just to comment on lighting, Ken, and that is that I won't be covering lighting today in our training course. There is a fantastic session that's been pre-recorded for you all that is available on the learning management system. So, Ken, handing over to you.
Thank you. And Marissa's about to jump into the learning management system to show everyone how to finish off the course. So she'll steal the screen. As she brings that up, just want to thank Jonathan. And
yes,
if you have questions for Jonathan that you didn't get to, and we're not going to get time to, feel free to reach out, and he's always happy to have a chat about some of those unique, specific design scenarios that you've got.
Absolutely. And sorry I was a bit croaky today, guys. Just getting a little bit under the weather, but I've come through fine for the course, so that's good.
Over to you, Marissa, to just show us how to finish.
Ken. Yeah, thank you. And thanks, everyone. Okay, so over in Module 2, we've got a lighting design video by Jamie Robertson, which is what Jonathan just referred to. So have a watch of that video. We've got another quiz for today, another multiple choice quiz. Hopefully no bugs with that one. We've checked it over, so fingers crossed. Okay, so just to finish off the course, complete your 2 quizzes, Module 1, Module 2 quiz. You do need to successfully pass those. Once you've done that, we've got just a short feedback form there. I would love to get your thoughts on the course. It is a new course, so please let us know if you have any suggestions for us. Once you've done that, we've got your certificate of completion there. As you complete your tasks and your feedback form, your certificate will become available for you to download. And just super quickly, we've got a kind of cool, handy, you're able to share with some badges that you can share on your LinkedIn or your Facebook. Just follow the links there, and you'll be able to share your achievements with your network.
Good. Thanks, everyone. And thanks
Just
for
on time.
all the questions. We've ticked over the hour now, but yeah, keep in contact. You've got our contact details. Any questions through to safesystemsolutions.com.au. So training@safesystemsolutions.com.au. Thanks again, Jonathan.
My pleasure, everyone.
We covered a lot, and we will see you at our next course.
Excellent. Thanks, guys. Okay.
See ya.